Hello, people of Earth. Can't resist a good iCarly reference, right? Welcome back, stats people. Here we go. Let's wrap this up. Again, I love the discussion, etc., but we also need to get through some material. So here we go. Let's talk about powers. Our power, not powers. Um, we'll talk through it, and hopefully it'll make some sense. National mean score in the math portion of the SAT is 511 with a standard deviation of 112. So notice we have what the standard deviation of our population is. It is believed that the WeGo students have a higher mean than the national average. To find out, we take a random sample of 8 students. To find their average, we will use the data to conduct a significance test with an alpha of 5%. So, hypothesize, hit pause when you want. Write out the appropriate hypothesis for the significance test. Define your parameters. Hey, welcome back from hitting pause. So, the null hypothesis is mu is equal to 511. Our alternate hypothesis is that we're looking for data saying that mu is actually bigger than 511. And mu equals the true mean score of WeGo SAT math tests. It's not probably as clean as I could write it, but it works. Suppose the mean SAT score at WeGo here is 535. That's going to be our alternative mu. Go to Statlet. Now, the Statlet doesn't have it there. I put one in Classroom. You'll see it, and I'll launch it right here. And we're going to enter this information that we have here. So again, that our mu value is that our alternate is 535, and that we've got a standard deviation of 120. I'm just doing that so I don't have to go back and forth. And we're going to have this thing called a power. I'm going to talk about that. The power is the probability, as it says here, that the significance test will find convincing evidence against the null with the information that you received. So the power is going to kind of figure out, okay, what are the chances of what we're going to see? So over here, we have the applet. And so what we're going to type in is this. And so we have a mean of 511. And we want mean bigger than that, so that's the alternative hypothesis. Our standard deviation here, come on, there we go, it's 120. Our n value is 8. And our alternative down over here is going to be 520, right? 535. So, the question now be, oops, closed it, sorry. Close my keyboard. All right, so now notice here we've got this power thing that says 0.140. And what this is doing, let me take a screenshot of this quick so I can draw on it appropriately. I'm going to do a new page here quick. Come on. You guys are stunned again at my professionalism, I know. Come on, there we go. New page. Notice what's going on here. These are two graphs, obviously. And if we go back here a page, notice here we've got a mean of 535 and we have a mean of 511. This one here, the top graph, has my mean of 511. What the power does is says, okay, now what would happen if instead of the mean that we think is right, what happens if the number that we're seeing, the 535, is actually the true mean that's going on? And the reason for that is now watch what happens, is that this part right here, this lines up over each other, but which one has a bigger area? This one has the bigger area. Okay, so I mean, it's a rather significant thought of us saying, okay, what happens if what we're seeing is the actual truth? What does that have to do with everything? Well, let's talk more about it. Come back here. So that power, so in this case here, we had a power of 0.14. So this probability is really the power. So this power number, and there's a big complicated formula that you can go through and do, and you don't necessarily need to know it, so letting computers or problems tell you is fine. So power is 14%. So that's telling you again, this is the probability that the significance test will find convincing evidence against the null. So this is saying that according to what we have right now, we have a 14% chance that based upon what we have, that the null hypothesis is going to fall, and the alternative hypothesis is going to be true. Okay. Now, in terms of the interpretation of this, what that means is this. So if the mean SAT score at WeGo is 535, there is a 14% probability there's a 14% probability of the tests giving convincing evidence for the alternative. So in some ways what you can do is you can look at this and you're going to say, all right, the alternative being mu is bigger than 511. So in some ways you can look at this and you're going to say, okay, well, if it's only a 14% chance, is it really worth taking a look at? And not that you wouldn't, but it's just one of those things you know going in that you're probably going to have a problem with this. Okay? So the question is, so you want to increase the power as much as possible. And there's a couple of different ways you can increase the power. Let me show you what those are. Okay? One of them, notice, is sample size as you look on your notes. So if you go over here to sample size, watch what happens here if I increase the sample size from 8 to, let's just say, 30, which is, you know, a good sample size. So if we do that and we hit update, our power now has gone from 14% to 29%. Because what happens when you increase the sample size? Standard deviation starts tightening up. That means that the difference between, I'm not going to be able to run on this, am I? No. The difference between the 511 and the 535 in terms of standard deviations is getting smaller. And since that's getting smaller, that means that the 535 is, seeing the 535 is more significant because it's harder to do because you've got more people to worry about. I mean, if we ran this up to even, let's say, 100 students, you've now jumped your power, your probability up to 63%. And the power is the one down the bottom. So notice now, and part of that, again, is because we're saying what's the probability that the mean that we're seeing is actually the true mean. So now we've got 63% of the, roughly 63% of the area over on the other side of that. So you keep messing with that. So that's one. So in terms of sample size, increase the sample size. Always good. Best way to get more accurate data is get more data. You can also increase alpha. Now, the thing about increasing alpha, remember what's happening. Alpha is saying that you're letting, what type of error is the type, you know, if you're increasing alpha, that's your type 1 error, right? That means that you're assuming the person's innocent, but you're sending them to jail. So usually it's not your best option. But if we do that, let's go back to our 8. Okay, so there's our 14%. If I increase the alpha, if I decrease it, look, it gets smaller, right? If I increase it, like, hey, we'll take 10% error. Hey, we'll take 20% error. The more error you're going to be accepting, the more likely you're going to get data that works. Why? Because you're casting a bigger net. I mean, in some ways you're casting a bigger net, or in this case, you're letting more. Let me put it this way. The net that you're casting is having bigger holes in it. Ooh, I like that. Somebody write that down. I'm going to patent that. Actually, I can't. I'll just put it in a podcast. So there's that. So you can increase alpha. And that's generally not what you want to do, but I mean, if you need to, you can. So we're going to increase alpha. Now, the only other thing that we haven't changed here, we can't change the standard deviation, because the standard deviation is going to be what it is for the population in this case. So I'm going to bring this back down to 0.05. What's the only other thing left we can change? We can't change the original mean. We can't change the sample, or we've already changed the sample size. We changed alpha. So what happens if I change this? If I go instead of 535, what happens if we have a 600 average out of those 8 people? Ooh, now we're definitely cooking. And why would that be? Well, again, think about what happens when we increase sample size. If we increase sample size, we're increasing the number of because the standard deviations go smaller. We're increasing the number of standard deviations. Let me go back to there. So if we're increasing the number of standard deviations, actually I take that back. This one would be, yeah, so there's that. So, here's 511. Here's 535. So if our standard deviation is, let's say, like 15, okay, standard deviation equals 15. So then I've got a difference of what? 535 minus 511. So our statistic here, so that's going to be about 1.7. Well, if I lower this number, obviously, this one right here, if that changes to, let's say, like a 10, this now goes to 2.4. So it makes sense that it's going to be more significant because you're more standard deviation away. The other way you can just do it is change this number. So, let's go back to the original here. Let's get rid of all the blue stuff. Whoa, get back here. Down, stop. Things are not behaving today. Would be to change this. What would happen again if this is 600? If a same standard deviation of 15 comes back in, or, I take that back, we know what the standard deviation was, 120. But by the time you scale it for 8, so you got 600, so now you're talking, that's almost, 89. So now this automatically goes up to, from 15, C5 would be 75, so this is almost 6 standard deviations away. And so that's why that would do it. And it's not so much increasing necessarily the mean. The important part here is going to be, where do we go? There we go. The alternative. So while you could increase the alternative mu value, we can increase the distance between the alternate mu, so the alternate mean, and the null hypothesis value. Actually, I'll even put the word value there. Because again, the bigger that gap is, the standard deviation being the same, you've got essentially more, the z value would increase, the t value would increase. So there's that, okay? And that's what you really need to know about for power. And most of the questions that they'll ask, if they ask you something specific about it, this is one of those topics where you just like, you can probably cut your losses and just saying, if you know the basics, you'll catch enough to know. These ideas right here are important. Sample size is always going to make things more accurate. Alpha level, if you increase that, so you're being less picky in terms of how much area you're letting through, is going to be helpful for that. It's going to increase that, and then the alternative mu distance. So big ideas here. Number 1, power interpretation. So if you assume the mean is true, assuming the true mean is blank. So you've got some sort of value for there. There is a blank probability of finding convincing evidence. Yes, I know I shortchanged convincing. For the alternative, whatever. And then here, so is, you can put a value here, you can put a value here, and then this right here is going to be your H sub A value. Now, interesting thing about the power. The power allows us to talk about, we've already talked about type 1 error, okay? And we've drawn this box before. We've got truth, and we have a decision. And so let's say the truth is the alternative hypothesis is true. This is the alternative hypothesis is true. Decision in the top box is going to be, we're going to reject the null hypothesis. And the bottom ones, we say we fail to reject the null hypothesis. So obviously, the two that we know, if H sub O, if the null hypothesis is true and we fail to reject it, that's good. That's what we want. Hey, you didn't do the crime. Great, we found you not guilty. Perfect. That's what you want. Hey, the person did the crime. Hey, we found you guilty. So the alternative hypothesis is true. That looks a little sketchy there. And we rejected the null hypothesis. That's good. Now we talked about the type 1 error. Type 1 is right here. Type 1 is how much error are you willing to take. So you're saying that the null hypothesis is true, but you're saying it's wrong. And so that is just going to simply be, type 1 is just your alpha level. How much error are you willing to accept? You're innocent, but we're going to send you to jail. Okay, the water's fine, but we're going to give everybody bottled water. Whatever. Type 2 error is down here. And type 2 error is again saying that the alternative is true, but you don't have enough evidence to say that the null hypothesis is false. So that's the type 2 error. And to calculate the type 2 error, it is basically it's the complement balance of the power. So in that first example there, we have a 16% chance of proving that it's right. Well, we have an 84% chance that with what we had, we could potentially know that the alternative hypothesis is true, but we can't reject the null hypothesis. Okay? And again, there are going to be times where you just can't help that. That's just the way things are set up or the data that you have. But it's an interesting thing. So let's see. I've got 4 minutes. Let's see what we can get through. Can a 6-month exercise program increase the total body mineral content? TBBMC. For young women, a team of researchers are planning to study and examine this question. Researchers, blah, blah, blah. Alternative hypothesis, a null hypothesis. So we're saying, okay, let's assume that nothing happens. And we're going to have the alternate that something does happen. Mu is the true mean percentage change, the TBBC. So the power of the test is to detect the mean increase of 1% using an alpha of 0.05 and n is 25 subjects is 80. Interpret this value. So this is going to say that assuming that the true mean percent so meaning that the true mean percent of change is 1%. Because again here, there's my mean increase. So assuming that that's the case, there is an 80% chance that the tests we run test gives convincing evidence for the alternative. That mu is bigger than 0. So type errors are pretty easy to find. Type 1 error we already have. Trust me, if you get type 1 error wrong when they give you what alpha is, I'm going to have some serious words with you. And I say that in a kind, fatherly sort of way. Type 2, it's going to be 1 minus your power, which means I've got 1 minus 0.8. So there's a 20% chance, since we have an 80% chance of disproving it, we have a 20% chance in there that, you know, we may find we're not going to find the evidence that we need, even though it's true. And lastly, my last 90 seconds here. Determine whether each of the following changes would increase or decrease the power of the test. Explain your answers. So, alpha is going down, right? So alpha is decreasing. If alpha decreases, that means the power is going to increase. So power decreases. When using a smaller alpha value. So it's going to make finding convincing evidence is harder. And if we go from n, we're increasing to 100 from 125, so that means that n is increasing, which means that obviously, as we said, the standard deviation is going to go, so this is going to increase the chances, so it's increasing the power. Wow, that's fun. So, larger sample increases our chances. All right, anyway, with that, I have to go teach algebra. Actually, I have to go watch and take a quiz. But anyway, I hope that helps. As I said, we're going to kind of keep the power questions kind of basic. So don't go way too worried about it. But we'll spend a couple days reviewing, and we'll be all set for the test. Talk to you Monday. Oh, and subscribe, like, smash the like button, notification button, etc., etc. Bye!